Hello, welcome to this lesson where we're going to take a look at power calculations for three-phase circuits. Now, in this lesson, we're going to focus primarily, in fact, exclusively on the Y to Y configuration, but doing it for the Y to delta is absolutely the same. So we're going to focus on YY, and as you're going to see, it's really simple. There's just a handful of really simple equations that you need to know in order to calculate average power, reactive power, and complex power. So let's just go ahead and get right into it with power calculations for three-phase circuits. All right, so let's take a look at the wye-connected load, and that's what we're going to use to make our power calculations in this lecture. So let's see, there's an A phase line that's got that impedance, Z sub A. Attach that common node, then we have a B phase with an impedance Z sub B, also attached to that common phase. And then we also have our C phase, also attached to that common node, and we'll call that impedance Z sub C. Remember that we have our current I, AA, our current I, BB. I really just call them what they are, I, C, comma, C. And then we've got some voltages. So the currents going through each phase, and then we have a voltage VA, a voltage VB, and a voltage V sub C. And then there's really just a handful of equations that we need to know in order to calculate our power. So the first thing is, and remember this is all for a balanced system. Remember we talked about what that means a couple videos ago. So the first thing is average power. So average power delivered to each phase. We're going to call that P for the phase. P sub phi is equal to the voltage at the phase times the current at the phase divided by the cosine of, remember, theta of V minus theta sub I. And we sort of usually just call that theta of the phase. And remember that, let's keep this, V sub phi is just equal to the real component. So for A, it'd be just the real component of VA or VB or VC. And the same thing for I. It's just the real component of the real component of the current for A and B and C. But we're going to stay focused on just the A sections, since they're all equal to each other. So if that's our average power delivered to each phase, then the total, what we'll call the total average power delivered to the load is just, we'll call it PT, and it's equal to, super simply, 3 times the average power delivered to each phase. And then next up, remember we had total real power in watts and total reactive power in VARs. So if we have total real power, that's our P, we're going to call it PT as well. And that's equal to 3 times v of the phase, I of the phase, cosine of the angle of the phase. And you notice that's exactly the same as the total average power. It's the exact same equation, it's just times 3. The only one that's different is the total reactive power. And that's given as Q sub T. And that's 3 voltage phase current of the phase times the sine of the angle of the phase. And that's given in magnetizing VARs. And then the final thing we need is the total complex power. Well, words. Total complex power, which we'll give as S of T, is just equal to 3 times the voltage times the current at the angle. And that's all we need to do. So let's quickly go ahead and work a little bit of an example. And we're going to use the same circuit as the YY example a couple of videos ago. And the important things that we got there is in that example, we figured out that the VA, the voltage drop across the A phase load, was equal to 115.2 at an angle of minus 1.19 degrees. And the current flowing through the A phase was 2.4 at an angle of minus 36.9 degrees in amps. And the first thing it asks us to do is calculate the average power delivered to each phase. So we're going to say we're looking for P sub phi. So remember that P sub phi is just equal to V sub phi times I sub phi times the cosine of the angle sub phi. Let's go ahead and calculate it. That's going to be 115.2 times 2.4 times the cosine of minus 1.19 degrees minus negative 36.9 degrees. That's given in watts. And if you punch that into your calculator, you're going to get that the average power delivered to each phase is approximately 225 watts. Next up, if we want to calculate the total average power delivered to the load, that's going to be PT is just equal to 3 times P sub phi. So PT is equal to 3 times 225 watts. Therefore, PT is equal to 675 watts. So the next thing I want to do is calculate the total complex power. No, not complex power, but the total reactive power. We'll do complex power next. Power absorbed by the load. That's our QT, and that's equal to 3 times V sub phi, I sub phi times the sine of theta sub phi, which is equal to QT is equal to 3 times 115.2 times 2.4 times the sine of minus 1.19 degrees minus negative 36.9 degrees gives us a total reactive power of 484 bars. Now what I want to do, the last thing, part D, total complex power dissipated in the load, or let's call it delivered, and that's given as ST is equal to, what do we have, 3 times V sub phi, I sub phi at an angle of theta sub phi. So that's going to be S of t is equal to 3 times 115.2 times 2.4 at an angle of negative 1.19 degrees minus negative 36.9 degrees is going to give us a complex power S of t equal to 829.4 at an angle of 35.7 degrees. And there we go. That is power calculations for three-phase circuits. So hopefully you saw them pretty simple, just a few really simple calculations that you have to do once you've already done the analysis like we talked about in the previous lessons. But once you have that voltage and that current that's dissipated in each phase of the load, it's all good. It's all pretty easy. So that's it for three-phase circuits. Three-phase circuits get like their own class all to themselves. Later on, if you're sort of interested in power distribution or power generation, we barely sort of scratch the surface of what three-phase circuits can do and how they're analyzed and designed. But we're going to move on now to something totally different. In the next lesson, we're going to start in chapter 12. We're going to start talking about the Laplace transform, where we're really going to get into like the punchline of the course. We're going to talk about frequency selective circuits. We're going to talk about how to build filters. So we're going to kind of start that discussion next time with our introduction to the Laplace transform. So as always, if you have any questions, comments, or concerns, please let me know. I'd be happy to answer your questions. And if not, I look forward to seeing you guys in the next lesson.